Hi guys, so let's do section 10.2 part 2. For this section I'm not going to do too much thinking about concepts and stuff like that. I think basically we've done some of that in section 10.2 part 1, and what we want to do here is just transition from building a confidence interval for a difference in means to doing a hypothesis test for a difference in means, okay? Which means comparing two means. All right. So I try and keep this video short. It will probably not be very short, but I'll try and keep it as short as possible. So I'm going to go over this stuff fairly rapidly. To do a two-sample t-test for the difference between two means, check conditions first. What are the conditions? Conditions are the same as for a two-sample t interval. Okay. For a difference in means. And then to test this is our null hypothesis, and usually for us this is 0. Okay, usually for us this is 0. I think there's maybe a homework question where this is not 0, it's like 5 or something like that, but usually for us we're saying that our null hypothesis is that mu1 minus mu2 is 0. Okay. And then we compute the two-sample t-statistic. Remember, for means, we're always doing t-procedures. There's the formula to come up with your t-statistic. And then find the probability of getting that t-statistic this large or larger in the direction of the specified alternative hypothesis. All right, same as all our hypothesis testing. Use a t-distribution with degrees of freedom approximated by technology. Okay, this is what we're going to do. Or the smaller of these two. So whatever your sample sizes are, you take the smaller sample size minus 1, you can use that as your degrees of freedom, or technology. We're going to take this approach again. We want to do the test on our calculator and use the technology approach to get our degrees of freedom. This is also nice because you don't have to work things backward like we did for the confidence interval, where you had to find t star by taking their degrees of freedom and working backwards. Okay, in this case you just plug stuff in and you get your t value, you get your p value, and you get your degrees of freedom, and all the standard hypothesis testing logic applies. If it's greater than, we're doing one-sided test. If it's less than, we're doing a one-sided test there. And if it's not equal to, it's a two-sided test. So it will have double the probability of the corresponding one-sided test. Okay? So, tip here again, when checking normality for any t procedure, you should make a graph on the paper. Okay? Don't talk about a graph abstractly that's happened somewhere else. Make the graph on your paper. So we'll do that here. Okay. So let's do example 1. It says, does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. Okay. The relationship was strongest for black men. Such observational studies do not establish causation. Researchers therefore designed a comparative experiment. So examination meaning observational study, like observing, maybe surveying, something like that. Okay, but this is chapter 4. Observational studies do not give causation. Okay, so we need to do an experiment. Okay, the subjects or volunteers in this case were 21 healthy black men who volunteered to take part in the experiment. They were randomly assigned to 2 groups. 10 of the men received a calcium supplement for 12 weeks, while the control group of 11 men received placebo. Okay. The experiment was double-blind. Hopefully you remember what that means. The response variable is the decrease in systolic blood pressure for a subject after 12 weeks in millimeters of mercury. An increase appears as a negative response. Here are the data. Okay. Increase appears as a negative response. Interesting. So if you had an increase in systolic blood pressure, you have a negative number. Okay. All right. So there's our data. The calcium group, the placebo group, 10 calcium people, 11 placebo people. All right, and here are their responses. So the negative numbers here means their blood pressure actually went up. 0 would mean it stayed the same, and a positive number means a decrease. So this is 7 millimeter decrease in mercury. Okay, yeah, that's it. So it's a bit tricky. Any case, it says, do the data provide sufficient evidence to conclude that calcium supplement reduces blood pressure more than placebo? Carry out an appropriate test. All right, so test. Even if they don't say carry out a test, you should do a test here to compare the two. You could do a confidence interval, I guess. That would also work. You'd have to do some explanation, maybe more than your normal conclusion for a confidence interval. But safer to do a test here, especially since we're asked to do a test. All right? So let's jump in and do that. So state, okay, we want to perform a test of the following hypotheses. So the null hypothesis is that mu1, you can say mu sub c, I guess, minus mu2, mu sub p for placebo, okay, is nothing. In other words, the calcium and placebo had no difference in their ability to affect blood pressure, okay? And then the alternative hypothesis is mu1 minus mu2. Now think about this carefully. If mu1 is my calcium, and I look at the numbers here, I'm trying to say that there should be a positive decrease in blood pressure. So that means that the mean of these numbers should be bigger than the mean of these numbers. Okay, so this would tell me that this would be greater than 0. That would show, if I find evidence for the alternative hypothesis, that would show that calcium is effective in decreasing systolic blood pressure. All right. Again, of course, now we have to define stuff. You can say let alpha be 0.05. And then we have to define stuff. So we say where mu sub 1 is, and what is it? It's the true mean decrease in systolic blood pressure for healthy black men like the ones in this study, like the ones in this study who take calcium. Okay, and then mu2 would be, please don't just do a bunch of dittos, the true mean decrease in systolic blood pressure for healthy black men like the ones in this study who took a placebo. Something like that. Okay? That's a long state step. Very important though to get at least completely get this correct. That's a huge problem if you get that wrong. Okay? Think about it carefully. Alright, so then plan. Same conditions, random, normal, independence. Okay. So let's do random condition. And we have this statement here. they were randomly assigned to 2 groups. Okay, we just say the volunteers were randomly assigned to treatment groups. Okay, and then normal. And you know that we have a problem here because our sample sizes are 10 and 11. Oh no. Okay, so you need to go and put the data in your calculator. Let me erase some of this stuff. I think what you should put in your calculator, I would call this list 1, I would call this list 2. Enter it in your calculator. And then make a box plot. Okay, remember the box plot that shows outliers. And if you make the box plot, I think you get this. I'm going to attempt to draw a stacked box plot here for you. So we do our scale. You probably should do a consistent scale, like -11, I think, is the minimum for one of them. So -11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. This is, oh man, I'm doing a great number line here. This is kind of tedious and maybe slightly annoying, but we have to do it. So 1, 2, 3, 4, 5, 6. Ooh, goes all the way up to 18. Wow, that's a big graph. Okay, so make sure that you use consistent scale. This was a big part of our chapter 1. Make sure you can do graphs properly. Okay, your displays have to be proper displays. And then let's say we do the calcium box plot up here, and we do the placebo box plot down here. Okay, so let's do the placebo. I think if you do that, you get a minimum of 11. You get a Q1 of -3 up here. Okay, you get a median of -1, and then you get a Q3 of 3. All right, so here's my IQR. All right, like that, and then you get a maximum of 12. I think that's what happened. Okay, for the placebo group. So that's not too bad. It's not too bad, right? And then you do calcium. For calcium, the minimum looked like it was -5. Okay, and the Q1 was the same at -3. Interesting. And then the median was 4. Okay, and the Q3 was 11, looks like. And maximum was 18. Okay, so here's my IQR, here's my min, and here's my max. Okay, and so now we have to talk about this. We said if sample size is less than 15, I should see symmetry. Okay, now I wouldn't quite call this symmetry, but it's also not too bad. If I'm looking at this distance here compared to this distance here, that's not too bad. Okay, both of them are not too bad. So I think, depending on how worried you are, you can write a statement about proceed with caution or something. I think I'll just write since both box plots for the distributions of calcium and placebo respectively show no outliers or strong skewness, okay, you could argue that there's not much skewness going on here, okay? We will assume that the normal condition is met. All right. Whoa. And then independence. And then if you do independence, what do we get for independence? So for independence, we have to say a few things. So I think I didn't even do this for my completed note sheet. But for independence, you want to make a statement like the groups are independent due to random assignment. And one subject's decrease, or let's just say change, let's not say decrease, one subject's change in systolic blood pressure is independent of another subject's, okay? Of another subject. And that seems reasonable. Okay? So you get independence between the groups from random assignment and independence within the group because my change in systolic blood pressure will have no impact on yours. Okay? Alright, then we want to do the do and conclude steps. So I realize I'm a little bit out of space here. Let me do the do step and maybe I'll squeeze the conclude step in somewhere else. So do. We're back here and we're saying this is my test statistic. So we want to calculate our test statistic and then calculate our p-value. So my test statistic is t equals x bar 1 minus x bar 2, sample means minus mu1 minus mu2, all over the standard deviation of the difference, which is S1 squared over N1 plus S sub 2 squared over N2. Alright? And plug that stuff in. So now you have to do, you have to calculate your difference in sample means. So you need to do in list 3, you need to do list 1 minus list 2 and then do 1 var stats on that. Okay, we've done this before, and what you get is a difference in sample means of 5 if you do 1 var stats. Minus, oh sorry, I'm lying. You get 5 is your sample mean for this data set. Okay, my x bar here is 5, and my x bar here is negative 0.273. Okay, so you plug those two in, 5 minus negative 0.273. Okay, that's my first set of parentheses, minus, and then we said our null hypothesis. Okay, this comes from the null hypothesis. We're assuming there is no difference. So calcium is no better than placebo. That's what that means. And then you do this, and S sub 1, we found the standard deviation here. If you do 1 var stats on this, you get S sub 1 is 8.743, and then here S sub 2, if you do that with 1 var stats, you get 5.901. Okay, so we plug that in and you get 8.743 squared over sample size 1 is 10 plus standard deviation of the second data set, which is 5.901 squared over 11. A lot of numbers there. I would not suggest entering that in your calculator like that. I would do what they have, which is do your test. Okay, do your test on the calculator. So stat tests, and then go to 2-sample t-test. Okay, 2-sample t-test. Make a note for yourself, 2-sample t-test. And we have the data already entered in list 1 and 2, so you can just use the data. Leave the frequencies at 1, and we're doing a greater than for our alternative hypothesis. And here we address pooled, okay, say pooled no, and I'll let you read that on your note sheet, but there's the answer as to why we don't do pooled, okay? So I'll let you think about that, but then you get from this, you get your answer, okay? So you may even choose to do the test before you need to plug in all these numbers. So let me give you a bit of a strategy here. Before you even need to plug in all these numbers, you can do the test on your calculator, and that will actually give you all these numbers that you need, okay? So that you don't have to do 1-var stats independently. So you can choose to do that too. All right, so you do the test, and then you get your t value, which is from here 1.604, okay? So my t value is 1.604 from your calculator, and this is with degrees of freedom 15.591. Okay, this comes from your calculator. There's no way you're going to make that up. If you use the n-1 idea, then this would be 9, but that's not what not where this comes from. This comes from this degrees of freedom, so you have to use that degrees of freedom. And then my p-value is the probability that my test statistic is greater or equal. Remember, alternative hypothesis is greater, so that's why we're going greater or equal. 1.604 is, and from that you get 0.0644. All right. So there's my do step. So I have my p-value, and now we know how to conclude. So I'm going to do the conclude step here, and then I'll erase it again, okay? And do the p-value. So conclude. Let's conclude. Since the p-value, which is equals to 0.0644, is greater than my significance level, which is 0.05, okay, we fail to reject the null hypothesis, okay? So if I don't reject the null hypothesis, then I don't have sufficient evidence to conclude that there is a difference, okay? So we say we don't have sufficient evidence to conclude that the difference in systolic blood pressure for black men who took calcium and those who took a placebo is greater than 0. Okay? All right. I think this can be stated a bit more clearly. We don't have sufficient evidence to conclude that the difference in reduction, I guess, in systolic blood pressure, yeah, for black men who took calcium and those who took placebo is greater than 0. Okay? So, okay, that's fine. Then we have to actually go here and add the real conclusion. Okay, so do the data provide evidence that a calcium supplement reduces blood pressure more than a placebo? Okay, we have to say we cannot conclude that calcium reduced blood pressure more than a placebo. All right. So that's the conclusion. So you did. This would be, you do an experiment and the experiment failed to give you the results you wanted. Okay. All right. That's a fairly complicated hypothesis test, I think. All right. That's fairly complicated. So please, if you have any questions, let me know. Let's do part B, and then I don't know if I'll do anything else on this note sheet with you. I think the rest of it you can just read, but let's do part B at least. Interpreting p-value is traditionally not the strongest part of students' tool set, okay? So it says interpret the p-value of 0.644 for the test in part A in context. Okay, context, very important. All right, so we say, assuming the null hypothesis is true. What does that mean? Assuming there's no difference in the reduction of systolic blood pressure. All right, this is a long sentence. Okay, assuming there is no difference in the reduction of systolic blood pressure for black men who took a placebo and those who took actually we should switch that, keep it the same order. Who took calcium, we should switch this and keep it in the same order, sorry. Who took calcium and those who took a placebo. Okay, so this is my null hypothesis, all of that. Assuming there's no difference in the reduction of systolic blood pressure for black men who took calcium and those who took placebo. That's my null hypothesis. So assuming the null hypothesis is true, okay, what does the p-value mean? The probability of getting a mean difference, okay, a mean difference in systolic blood pressure of, now we have to talk about what we got. We got this. This is our difference. Okay, our sample mean difference is this number. Okay, which is actually adding. So it's 5.0273 of 5.0273 or larger. Remember our alternative hypothesis, we're following this, okay? Or larger. This comes from the alternative hypothesis, which is greater than, and it follows through, okay? So, getting a mean difference in systolic blood pressure of so much or larger just by chance is, and that's what the p-value is, 0.0644. Alright? So, assuming the null hypothesis is true, this whole thing is the null hypothesis. The probability of getting a mean difference in systolic blood pressure like the one we got, or larger, just by chance, is the p-value. Okay? That's also pretty tricky. Pretty tricky stuff to word correctly and keep all your numbers straight. Alright, so I think that concludes our notes here for today. I don't really want to do too much else. This is kind of in reverse order. I'm not really sure why the textbook chose to do this. I should have changed my note sheet, actually. This says using two sample procedures wisely, and then it talks about experiments. And again, it talks about a randomization distribution. Okay, so a randomization distribution is very different from a sampling distribution, the process of creating it, but in the end, it works very similarly. So a sampling distribution for a difference in sample means is very, very similar to a randomization distribution for a difference in sample means. And so you still get, if each one is approximately normal, then you get your randomization distribution of the difference in means is also approximately normal, and it works just very, very similarly, the results you get to a difference in means for a sampling distribution. Okay, so we already did this. We just did it right here. We just assumed that the normal condition is the same. It just works the same because this is an experiment. Okay, so there's a lot there. This is a huge topic by itself, but that's not really part of our course. Okay, the textbook doesn't go into that much either. All right, and so there's the conclusion for a randomization distribution, and then here it says, example 2. Decide whether I should do a paired T procedure or a two-sample T procedure. So a paired T procedure comes from matched pairs study design. Okay, this is chapter 4. And a two-sample T procedure means I took two independent random samples. Or I did an experiment with two independent treatment groups. So in our example here, sorry for all the scrolling, in our example here, we had two independent treatment groups. Okay, that's why this is a two-sample T procedure. Oh, I realized we didn't name the procedure here. Okay, this is a two-sample T test for mu1 minus mu2. Wow, I realized I didn't name the procedure. I would fail my own test. Okay, any case. So there's that. So that's the only thing you have to consider. Which procedure would I use? Is it a matched pairs design, or is it literally two separate independent samples that were taken? So two independent samples. Okay. So if you read the first one, it talks very clearly about matching tires to an axle. Okay. You're matching two tires to each car in the rear, and you're randomly deciding which side of the axle gets which tire. So this is definitely matched pairs design, and therefore you would use a paired T procedure here. Okay, this is not too difficult. And then 20 factory workers agree to take part in a study. Researchers randomly assign 10 workers to do a repetitive task and 10 workers to do a task in silence. That's two independent groups. So because I have two independent groups like an experiment, let me write groups. This would definitely be a two-sample T procedure. Okay, two-sample T procedure. Okay, so if you can identify two independent samples, groups, treatment groups, or groups that were sampled, it's a two-sample T procedure. If your prompt or your study describes a matched pairs design study, then it's a paired T procedure. Okay, and the calculator stuff, I don't think that's too difficult. You can figure that out, and there's the homework. All right, thanks, guys.